So this is kind of like more of a practical kind of overview of user studies, and this is kind of from a lecture that I usually teach for the CS departments, mostly relevant there, where we are discussing like how to basically set up a study where you have like a user like we have a human-computer interface where you train or you try to use human data to understand like if the person is engaged in the interaction, or if they're distracted, if they're healthy, or if they have some certain needs, etc. So this is more relevant there, but I think a lot of the stuff here can be applied to in machine learning. I try to make it more relevant to the machine learning in general rather than like these user studies. Basically, just a brief overview of like what this kind of slide deck is about. Well, basically we're interested in the importance of user studies, like why we want to do that. We have some basic vocabulary that we want to talk about. And then we go through an example that I kind of like. I think we talked about like data visualization a lot before, or not that much, but a little bit before. I'll just reiterate on that, and then we're going to talk about some statistical tests. And then later, I would like to also mostly talk about Integrator Agreement, and I think this actually becomes more and more of a difficult problem in machine learning, because while we have often like loads of data available to us through, for example, YouTube or just like general web crawling, where we download tons of data, but you actually don't really have annotations, and you don't have labels for them. And one way to get these labels is through basically pushing these data sets onto like platforms like Crowdflower, Mechanical Turk, etc. But then you don't have access to those people personally. You don't know who they are. You pay them a little bit of money, but it's not very much money. And like, how do you make sure that they actually did the job right? Like, how do you evaluate if multiple people agree upon a certain type of decision? And so these are kind of like a couple of examples of how to evaluate that. We can go into more details on like how to set up these studies if there's some need, because we have quite some experience in running these Mechanical Turk studies, where you can train the Turkers. You can first like define like a certain pool of individuals that you trust. You can reuse that pool if you want to, but then also you can insert into your like form, in the web form that you post them. You can insert these kind of like trick questions. Like, for example, one of the trick questions that we use is basically one of them says so you have to fill in your demographics as a Turker, so you like male, female, age, etc. But then it says we do not need your information about your education. Please do not fill in the following question. And then there's like a question about education, like did you graduate from college, etc. And then they have to like ignore that question, right? And so we know that people that don't ignore that question didn't really read the instructions at all. So stuff like that. Or one of the things that we do is if we have like listening tests, and we say, okay, so listen to this, like, do you think this conversation is going well, or this conversation is going badly? Then we sometimes replace the audio with like, do not rate this question. This is just an attention check. And then it's only in the audio, but in the written text you still see, okay, like rate this question and so on. So you can do all these kinds of tricks to try to identify who is paying attention, who is not. But there are, there's some real like caveats with generating these large data sets. But I think if you pay attention all the way, you can get really some good quality data through these methods for a cheap price. Like we, for example, pay individuals, like for each of these human intelligence tasks, like called hits on MTurk, we pay sometimes like 10 cents or 5 cents to a person. But it's not more than like 20 seconds or 30 seconds of So that, and if you do more tasks in a row, you can speed up as a turco as well. So that's kind of like a good way to like move this forward and quicker, and like generate loads of data. Okay, so learning goals and basically some basic understanding of user studies, some important vocabulary, dependent, independent variables. I'm going to talk about statistics and visualizations, and then how we can use these to infer some findings. One of the fun quotes that I like to use is like, so when you do research, you don't want to do the following. You don't want to use statistics as a drunken man uses a lamppost for support rather than illumination. So you don't want to like support your findings just through statistics, but you actually want to understand your findings through statistics. You want to like basically like further shed light onto like what you are investigating, rather than just like claiming something that happened and then like just use statistics to prove, oh yeah, this is like this supports this enough, this is happening. But also try to like basically infer some further knowledge from the statistics that you're using. All right, and there I have a couple of like fun comics about p-values, for example, which is like a big interesting pet peeve. So why are we conducting studies? Well, they are in general like a basic and essential component of quantitative research. Like you want to, for example, like if you're not the person that does, for example, like qualitative research, like anthropologists do, or like some human-computer interaction like researchers do, like you don't necessarily want to sit down and interview the individual after they interacted with a program and find out, oh, like how do you find this? Like, oh, you removed your Fitbit after a month of usage. Why was that? Like, you can do that. That's qualitative research. You can ask them about these experiences. But user studies are very important in quantitative research as well. So you want to basically compare different types of approaches, solutions. You want to provide quantitative figures, like you want to say this is like individuals preferred this product over that product, and you want to assign certain numbers to that. You don't just want to say, oh well, like that person said it's great, but that person said the other product is good, so they prefer that one. So you don't want to compare qualitative differences, but you want to quantify what you observe. And you want to reveal scientific findings rather than personal opinions. And so examples, and I think these are like just examples that I came up with. Is like, so smoking increases the risk of lung cancer. That's a scientific finding. Behind that scientific finding obviously are statistical tests. There are numbers associated to that. There are like very thorough research studies in there. And I would like to talk about a little bit like what goes into a statement or a scientific finding like this further. Or another finding would be, for example, sequential models outperform support vector machines in speech recognition, right? And so like that is, for example, like a statement that could be used in machine learning, where in the case of speech recognition, you don't just want to like investigate like every frame separately, because there's obviously a temporal dependency. So you have like like more of a sequence that you want to classify. So obviously like sequence classifiers will be better than support vector machines, but that has been shown in many experiments. So you can compare different types of classifiers with statistical analysis as well. 90% of subjects prefer robot A over robot B. Bloggers posting negative opinions frown significantly more. This is kind of like a multimodal thing that we have investigated. So there are different types of user studies. So one case is correlational studies or observational studies, where basically you observe a study population and we don't put any manipulation on there. They describe behavior, like look for relationships between variables, yeah, so one of the examples here would be the vlogger example, where you basically, for example, you can download 1,000 vlogs from YouTube, and then you can look at, okay, so which vloggers talk about negative stuff, like who is against something, and then you look at their facial expressions. There's always a correlation between, or you can possibly identify a correlation between that, but you can't identify a causation through this observational study. You didn't hold all the variables constant, and we're going to have a couple of examples there. And these experimental studies are the ones where you actually try to hold all the constants, all the variables constant. And a couple important staples of this is, like, you have to randomly assign subjects into groups, and you have, most of the time you have two groups. You have a treatment group where you change the interaction in a certain way, or you change this is kind of like the variable that you want to investigate, and you only change that variable, and you keep everything the same in the control group, and just don't have that variable, for example, be the baseline. And we're going to have some examples for that. This, in effect, then allows you to study cause and effect relationships, and obviously there are different types of use cases between those. And this is kind of like an important caveat here. Correlation does not imply causation. This is very important to keep that in mind. So if you don't design the study yourself, if you don't hold all the variables constant between two groups or multiple groups that you want to test different types of variables with, so for example, you don't have to just have two groups. You could have SVMs, LSTMs, neural networks, and naive Bayes. And you have 4 groups, but you held everything else constant. You didn't use 5,000 sentences of training for one and only 200 for the other, because that obviously would change your approach, right? Like the variables are different. If you give one classifier an unfair advantage with more data over the other classifier, you can't compare them. So you have to keep everything else constant. And if you compare, for example, machine learning algorithms, you might actually also want to kind of keep the so if there is a chance to actually use the same initialization for all of them, you want to use the same split for training and test data for all of them if possible. That's why I always recommend to start off with defining for yourself before you do anything, this is my training set, this is my validation set, and this is my test set. And then you can play around with the training and the validation set, but you should, if at all possible, not touch the test set anymore. Just keep that constant so that you can actually compare your approaches against that one test set that you kept out at the very beginning. And then you should be careful about how you select that. You should not, you could be unlucky and only select negative examples for the test set. Try not to do that. You should try not to, for example, if you're interested in human behavior, like facial expression recognition, you don't want to have necessarily the same people in the test set as you have in the training set if you want to investigate generalization capabilities and so on. So there's these important considerations. So here are a bunch of examples for user studies. I don't really want to talk too much about them, but it's just kind of for you to go through, to get some ideas and some thoughts about this. We scientists, we always want to kind of understand cause and effect relationships, and so there are a couple of important prerequisites. So a cause has to precede the effect. So and the effect cannot come before the cause, because obviously that like temporal relationship is a bit difficult to explain that. Cause and effect should be correlated, but not just correlated, and you need to make sure that all other explanations of the cause and effect relationships must be ruled out. So actually there's an interesting paper that I've seen recently where so the classification task is to identify from two streams of data points which one is the cause and which one is the effect. And that paper, for example, investigated so which one is the cause and effect when you observe temperature and you have the actual altitude above sea level for the measuring station of the temperature. So you have the weather station somewhere on a mountain or somewhere down at sea level, and you measure temperature. And obviously the higher you're up in altitude, the lower the temperature is going to be. And but it's not like the lower the temperature, the higher, like, so that's not causing you to move up, right? Like, and so they had like 100 of these examples from different like sensors where you have one variable and one cause and one effect, and the machine learning algorithm had to find out like which one's the cause and which one's the effect from that data set. And I think they were 70% accurate, which if like a human obviously knows what the variables represent is easy for a human, but like if they don't know, like they can't really do that. It's kind of funny. I don't know how they actually did it. It's like a pretty long paper, but it was very interesting. All right. To infer causality, we need to kind of have like two control conditions, where we have the experimental or the treatment condition and the control condition, and we need to make sure that all the other variables kind of like are equal between the two. So in machine learning, we often observe the effects to infer the cause. Okay, and for us to be able to kind of talk about this is like we need to identify what a dependent variable is and what the independent variables are. And so the dependent variable is basically the variable that we are measuring that we want to see the effect on. So for example, the dependent variable in the vlogging example would be the amount of smile or frown levels in the person that speaks. And the independent variable would be basically the amount of negative words that they're using. Okay, but that's, again, as we said, it's kind of like this observational study. But in a study where we would control the setup fully, we would say the independent variable would be like which robot people interact with, robot A or robot B, and then the dependent variable would be what we measure there, like is the robot A more engaging or less engaging, and the dependent variable there could be like the behavior that the people interacting with the robot exhibit, or like what they fill in, like in the questionnaires and so on. Okay, an independent variable could also be the gender, and so on. So depending on like what we want to study, and here are a couple of examples. So the dependent variable is the measured one, and the independent variable is a controlled variable that you want to control or manipulate. Here are a couple of examples. So you want to investigate how stress affects the heart rate in humans. The dependent variable is heart rate, and the independent variable is the amount of stress, and so on. Okay, so like you can try to think about other variables yourself as well. Okay, we can then also, if we like know what we are, or actually this slide might be important to have like earlier before we talk about like user studies or whatever, but I think it's very difficult to formulate actual like real research hypothesis. So you want to make sure that you understand your problem fully. So in order to be able to set like a real research hypothesis, and So you want to basically state in the hypothesis what you're going to investigate, and then if you know exactly what you want to investigate, it's very easy to actually set up a user study. So for example here, regular vitamin C intake is prolonging the life of humans. Depressed humans, or like the other one is like depressed humans exhibit lower pitch variability. That could be a hypothesis, and importantly, behind, for example, like the depressed humans exhibit lower pitch variability, well, there is some like train of thought behind there. So you would have to go into the literature and say, okay, so literature explains the following things. So you have, for example, depressed individuals are often like considered to be more monotonous, and like how is that, right? Like, okay, so clinicians actually subjectively identified that individuals that suffer from depression seem to be more monotonous, less expressive, etc. But then that's a subjective observation. So that a subjective observation motivates me as a researcher, for example, to try to find an actual quantitative assessment or a quantitative variable that correlates with those subjective observations. So I have, for example, looked at pitch variability with respect to depression. Important to note here is like not every hypothesis will actually be correct, right? That's why it's called a hypothesis. You can make mistakes, right? But it's very tempting to formulate your hypothesis after you've done your research. It's very easy to come up with hypotheses then, right? But like you want to, if at all possible, have your hypothesis before you go in. And I think for like social sciences, they have like now servers where you have to submit your studies beforehand, before you even submit your grant, and like you have the study record in the server, you submitted your grant, you get your money, and then now you have to conduct your experiments as you proposed in the grant, and then you have to compare it to your previously stated hypothesis. They have a timestamp there, right? And so I think there's still ways around that. You can like basically run your study before you state your hypothesis again, but that like the timeline starts to become prohibitive in that case. But like yeah, so you want to kind of like follow this path here, like where you first formulate your hypothesis, and here is like prior work, your prior work, literature, your data sets, and so on. Like what's in your data, what you want to investigate. Formulate the hypothesis, identify dependent, independent variables, and then choose an appropriate experimental design. Typically, and this is less important for you guys, I think, but typically in user studies we have within subject designs as well as between subject designs. So within subject design is very easy. You have two systems that a person needs to interact with, and you want to find out like which one's better. You have them interact with A, then you have to interact them with B. And then you identify, okay, the same person worked with both systems, which did they like better, right? And then between subjects, you just have a bunch of people interact with A, and then another bunch of people that are separate from each other interact with B. Now there's like a couple of tricks here, right? Like, okay, so how do you randomly allocate people into these two groups? Who interacts with A, who interacts with B? You need to be careful there to balance that out. You can't just have everybody under 18 interact with A and everybody over 35 interact with B. So that would be obviously like a weird effect there. The same thing here for within subjects. For example, you can't just have everybody first interact with A and then everybody interacts with B, right? Unless that is really, really required to have that separation. You want to like balance out ordering effects, for example, and so on. So there's many things that you have to kind of consider in these cases. All right. So what is this? Yeah, just make sure that you randomize your subject groups and like just don't do these weird things. One of the other considerations actually is like, okay, so when you measure something, you want to have like two kind of things present. So first, one thing that you want to have present is like you want to make it reliable. Or you want to have measures that are reliable. Like if I use my camera today, or if I use it tomorrow, or if I use it in the morning, versus I record people at night in the other condition. I think one of the most famous examples was like a DARPA project where they tried to identify tanks in pictures. And the funny part was that they went out to photograph tanks in forests and like wood and stuff. And they went out one day, they recorded all the non-tank pictures. And then they went out another day and they recorded all the tank pictures. And what the classifiers did, they recognized the weather. It was cloudy one, and the other one it was not cloudy. And so that was kind of like one of the stupid mistakes that they did. So even in your data collection, you need to make sure that you have like reliable and consistency there. And then there's another consideration about validity, and there's two validity considerations. Internal validity, which is like accurate and robust measures, experimental and control group have to be the same-ish. So you can't just have, as I said, like young people in one group and older people in the other group. That would not be considering like that would not be good internal validity. But then the other consideration is also the external validity. So if you want to make a claim about humanity loves robot A better than robot B, like that might be a bit strong because you have not had humanity interact with either robot. But if you have a representative group of those, of humanity or population X or population Y, then you can make those claims for that population. But as for example, one of the things that you might know is well, all these psychological studies are basically studies of undergrad behaviors. Like most of the studies have been run on students, and well, because we can enlist students for free and basically tell them if you don't do this, you don't get credit for something. So like it's. But then to say that the experiment holds for the general population is wrong, right? Because student populations are very, very specific populations. It's young people, it's smart people, it's like bored people, I don't know. But yeah, so it has a very different, and the psychological state of students is often very different from individuals that you recruit, for example, from Craigslist, and that's something that we have observed in the past. Okay? Just a list of confounding factors or problems. There are a list of biases here on Wikipedia that you can think of. Experimental bias, systematic bias. Like you might sometimes make mistakes. Systematic bias sometimes, like in machine learning, are not that bad. Like if you, for example, in your extracted data, every value is like times 10. Doesn't really matter, like if it's the same for all the experiments. So that's a systematic bias that might like prohibit you from making certain claims about your data, but doesn't make you or doesn't prohibit you to make a claim about like which classifier is better or worse, something like that. So there are different kinds of biases here. I have a cool example study that I would like to talk about. It's kind of like my favorite. So this is, I think, is like one of the most famous papers that came out of my old university. It's not the computer science department, it's the biology department. And so it went to the Science magazine, which obviously is one of the most prestigious scientific outlets. And so the research hypothesis is kind of cool. So so the hypothesis in the paper is ants measure distance traveled by using some kind of step integrator or step counter. So they basically, so ants to come back from a food source to the nest use a step counter. They count steps. That's what their hypothesis is. And In other words, ants with elongated stilts or shortened stumps take longer or shorter strides respectively and concomitantly misgauge travel distance. Travel distance is overestimated by experimental animals walking on stilts and underestimated by animals walking on stumps. So if you have stilts, your stride is longer, so like you should actually overshoot the nest, and if you have stumps, your stride is shorter, and so you should undershoot the nest. And they identified dependent and independent variables. Dependent variable was the distance traveled by the ants, and the independent variables was the length of the ants' legs. And in one case they cut off half of the legs for the ants, and in the other case they glued some stuff onto the legs. This looks like this. So this is how that kind of looks like. So these guys have stilts, and these guys have like only half legs. And then they painted them red and green, and that poor ants. So the normal ones, and so just to make that clear, in a sense, so what they did is the ants have like their nest here, or their hive, I don't know what it's called, and they go explore, right? And they go explore and find a source of food that the researchers have planted somewhere here, right? So there's a distance that you have between the nest and the food source. And at the food source, they pick out the ants and cut off their legs, or add the legs, and then they put them at a new food source in like a rail thing, right? So that they can measure like the distance that they travel, and obviously the nest is not at the other side of the rail, but they put them into the rail and then looked how far they walked, and basically found that the guys that walk on stumps are walking not far enough to the nest, which is 10 meters away, and the ones on stilts are actually walking further. The ones that are normal, they walk the right distance and look for the nest in that area. And so that's kind of like what they found out there. And the statistical evaluation that they did basically is the following. So they have like some numbers to this. They have different ends. So these are the number of observations in each of the categories, and this is the statistical p-value. So this is highly significant. And they probably did an Anovas test between the groups first, and then identify like, okay, where are the single pairwise comparisons and so on. And we're going to talk about this in a second. Yeah, and so the scientific statement is like, desert ants calculate the distance traveled by counting their steps. That's kind of like a fun study, I think. Yeah, so you can think about that at home, I guess. And I think we talked about this at length before. I like these visualizations. They're kind of cool. And I think you should probably think about such visualizations in your own studies, and like try to see if you can come up with certain experiments or certain experimental evaluations that are meaningful, that let you arrive at a certain scientific statement and so on. Okay, so now we can actually also talk about statistical testing. In statistical testing, one of the things that we want to do is we want to compare performance of, or like whatever, dependent variable A versus dependent variable B, and most of them are like, we often assume they are normally distributed, so they follow some like kind of Gaussian distribution, and we can have different kinds of cases. So in this case, we have like in test 1, we have this kind of separation between A and B, and in test 2, we have this sort of separation between A and B. So if we went ahead and said like, oh well, the mean value for this one is, I don't know, like 2, and the mean value for this one is 4, and the same for the mean value for this one is 2, and the mean value for this one is 4. And so we would say, okay, like they have the same distance. This one, if this is like an error measure, would be better than this one. The same here. Red is better than blue. But the problem is that there is obviously something different between the two, and it's not enough to just measure the distance between the mean values of certain observations. We also need to take into account the standard deviations of these distributions, and obviously there's a lot less overlap between red and blue in this case than between red and blue in that case. And what we often want to do is we want to know, or we only want to say that one is significantly better than the other if there is only very little chance that their performance or the values are actually going to be the same. So we want to measure how unlikely it is that what we observe to be a difference is actually a difference by chance, or is a difference by the independent variable that we chose. So for example, does classifier SVM outperform classifier HMM? So you would run, I don't know, 10-fold cross-validation for each cases. So you get 10 values that measure the performance of SVM and 10 measures that measure the performance of HMM. If you find a separation as such, you would say SVM significantly outperforms HMM. If you have an observation as such, you're not able to say that. You're like, okay, well, on average, maybe SVM is better than HMM, but it's not significant, right? So there's no statistical test that supports your finding. And there are other examples of what we want to conduct. So what we want to do is we want to know if two samples, so this is a sample distribution, are statistically significantly, if the difference that we observe is unlikely to have occurred by chance. And word of caution, we do not use the word significant if we don't mean statistically significant. That's kind of like just a convention that I like to keep for scientific papers. You can use other words like tremendous or
Big league?
what?
Big league?
Big league. Big league. The difference is big league, but don't use significant. So what we now need to understand is kind of like how do we test for significant differences, okay? And well, there are two types of tests. Most of the time, if you don't know anything about your distributions or about your data sample, use non-parametric tests where, for example, you are doing like a rank sum test or a Mann-Whitney-U test and so on, where like the data distribution does not follow certain, like, and we had that parametric classifiers versus non-parametric classifiers. If you don't know anything about your data, don't necessarily use t-tests or Anovas, because they assume that your data is actually normally distributed. But there are ways to find out if they're normally distributed. So you can actually do a normality test beforehand. And for the project, I know that t-tests and Anovas are much more common, and I think we're going to be like just fine by using them. But just as a word of caution, there is a difference between parametric and non-parametric tests. So if you don't know anything about the distribution, don't necessarily use parametric tests. If you know a lot about them, you can use them. If you know that, for example, the data is normally distributed, you can use a t-test or ANOVA. And they're very easy to use. You find t-tests in R, in SPSS, in MATLAB, in Python. I think SciPy has it. And so, like, they are commodities. Like, really, like you can, and there are thousands of examples on how to use that. And most importantly, there are also very many examples, and I should have put that up, very many examples about how to report the results. it's not sufficient to just say with p smaller than 0.05, but you have to like add the mean value that you observed, the standard deviation, the t-value that you observed, the degrees of freedom that you had. So that also explains like how large your data set is. And one example that I like to give here is well, like I think we can quickly try that out. The number of observations that you have in your data set is very important in order to understand what the statistical test gives you. So like I think it's a bit difficult to explain like this, but so if I go to MATLAB and say I want to have a distribution, a random distribution of 100 numbers. Is that correct? Yeah. So I have 100 random numbers. So I could do hist x. Looks like it's not great. Well, it's oh, it is actually equally distributed. Let me normally distributed. Now this, okay, so normally distributed. So now we have a normal distribution, we sampled 100 values, okay? So this is what we have in X. So to create our new variable, Y now, we just add, so we shift that distribution by a little bit, okay? So, and that little bit could be, for example, 0.1, right? Or it could be 0.05. And now we can do a t-test, and then this gives us our hypothesis, like yes or no, and our p-value is equal to t-test y comma x, right? And so in this case, there's no statistical difference between those two numbers, or two values, okay? So if we run this again with, with a larger difference, so I don't know, suffice. Probably this is enough. And if we run this again, oh, now it's significant. But that is significant because 4 times more distance is between those two numbers, okay? So let's run this again, but this time we do a much smaller effect, right? But now let's do maybe 100,000 numbers, right? And I do the same thing here. I just add, a couple of zeros here, and I do a test. And it's very close. Okay, maybe we should have used 110,000. But anyways, so you can see that the more data points I have, the more fine-grained of a difference I can measure, and I will find statistical significant differences. So that it is very important to actually mention the number of observations that go into these calculations when you get a p-value. If you have thousands and thousands and thousands of data points, and you do a t-test and you only report the p-value, I don't know nothing about what you did, right? Like there's no, I don't fully understand what the result is because I don't have all the information that I need to make that assumption, okay, or that assessment. So that's very important to actually report these results also in an appropriate way, which includes mean value, standard deviation, p-value, degrees of freedom, number of observations that go into it, and so on. Okay. These are typical. So this is a typical t-test, and the t-test, I think most of you know that, like basically both samples have to be normally distributed, and like what we want to do is we want to measure if x and y have a different mean value, okay? And hypothesis 0 is basically they have both have the same mean value, and hypothesis 1 is they have a different mean value. That's all we can measure. We don't measure like, oh, x is larger than y, or like x's mean value is larger than y. We need to know the mean values to know that. The t-test only gives us, yeah, there's a difference, right? Then there are different types of t-tests. One sample t-test, like if you only have a sample x, you could, for example, measure it's significantly better than 0, or like larger than 0. Then you have paired t-tests, where it would be, for example, within subject design, where you have, for each value in your list, you have a corresponding value at the same location in that list. And unpaired t-tests, where you just have between subject, where you have like no ordering between them. Okay, here's an example. You can also do Anovas, and Anovas basically is an analysis of variance, which basically only tells you in hypothesis 0, all groups have the same, or like are sampled from the same population. That's the hypothesis 0. And hypothesis 1 is one or more samples are drawn from a different distribution. But you don't know which ones are different from each other. So you need to do follow-up tests and identifying, okay, group stilts is different from normal, or group stilts is only different from the ones with the stumps, and so on. So you need to do these pairwise comparisons. And there's a great example here that you can do, and I would really recommend trying this out. So basically, we can quickly do that. It should be fairly easy. So I loaded it. Then I want to like do a box plot. Okay. Anyways, so the box plot doesn't work, but that's fine. And in MATLAB you get what? Fine. So I'll just fill in the rest. So we get this, so we have some box plots here, that's kind of cool. So MATLAB gives you this. So you have Setosa, versicolor, and Virginica, and then you have your degrees of freedom, which are in Anovas. You have 2 values for degrees of freedom. 2 basically tells you how many groups you had, and it's 3. It's like 2 plus 1, and then you have 147 observations distributed between the 3. And then you get an F value, which is important. You need to report that one, and then you need to report this P value here, which is it's very small in this case. And the cool thing now is that you also have this variable here that's called stats, which is displayed down here. You can, with this, you can call this function, which is called multcompare, which now allows you to do some cool post hoc comparisons where you can actually, so I clicked that one, so you see this is the confidence interval boundaries here. You can click that guy. Usually, why is it not working? It used to work that you can click these and then you see the differences. It's kind of fun. And then if these are, for example, if these lines are overlapping between 2, then you see that they are not statistically significantly different from each other. But maybe there is a difference between number 1 and number 3, but not between number 1 and number 2. Okay, so that's kind of like some stuff that you can investigate here. Okay, all right. Let's continue. And here we have the same example in R, so you can try that out as well if you want to. Now, as I promised, there is also a comic about p-values. So this is how you report p-values. So first of all, whenever you have p-values that are smaller than 0.4, you claim that they are highly significantly different. if you have significant results like such, and then if you have just 0.05, well, you rerun your experiments and hope that it comes out the other way now. You're like on the edge of significance, highly suggestive, significant at a p-value of 0.10, and this is interesting subgroup analysis in this case, or like yeah, it's probably significant at 0.2 or something like that. So obviously this is a joke. If you have p-values that are like not that significant, don't try to fake it like it's fine. just report what you find. It's probably still interesting. Yeah, I mean, like people call this stuff like a trend and like, oh, it's approaching significance. I think I have also been guilty of that before. Nobody's gonna like expel you from science in general, but it is kind of interesting if you see meta studies, like how many results and papers are published that actually have like a p-value of like this, right? I mean, like it's insane. Like, and so the p-value of 0.05 is actually like it's a hard threshold. If you're above that, it's not significant. If you're below that, it's significant. And obviously that has problems, right? Like it's like 0.051 is not much worse than 0.049, but it's convention that at some point it's like, okay, it shouldn't be more than 0.05. So yeah, I don't know, like it's yeah. So if you use this, for example, it gets into the lamppost area sometimes, and like yeah, it's similar to distributions of grades sometimes, that we have like everybody in the A column or everybody just before the F column. But and I think we're gonna be all mostly on the better side of this. Okay, so but this is kind of like just as a yeah, don't try to fake results ever, and I think it's not worth it. So for measuring inter-rater, so now I'd like to talk a little bit about measuring inter-rater agreement, and this is often used like in affective computing, sentiment analysis, emotional cognition, and loads of other topics. But this is the area that I kind of work on. And so in this area, like to understand the emotion of a person, you have basically three ways to do that. You drill a hole in their head and you ask, like you look in, like see what they think. You ask them after, during, etc., the experience, how they feel. And that might be interruptive as well. Or what we often do, if the data is already recorded, we ask other people about the opinion of them on something like this. Like, so they see a video and like, okay, what do you think about this video? Are they happy? Are they sad? Are they angry? Are they depressed? And so on. And obviously everybody that has an opinion comes with like a bag of other things, like a bag of variables on their shoulders. So for example, maybe somebody didn't pay attention that much on the audio, but only looked at the video, so they might see something different than they heard. So the perception is a problem. Maybe their quality when they listened to it online wasn't that great. Maybe they were in a like a coffee shop or whatever. So their perception might be impaired by something. But also they also might have like stood up or woke up with like a depressed mood and say, oh God, I have to do this MTurk stuff again. So they might bring in like a negative mood and rate the experiences in a different way than somebody that woke up like, oh my God, MTurk, yes. It's like finally I make 10 cents more. And so that influences you as well. And you want to identify, like, however, like if people have opinions, you want to measure like, how much do they agree on a certain item or a certain data point. And if they agree a lot, you want to keep that data point maybe in your data set, and if they disagree a lot, you might want to investigate that a little bit further and try to understand what's really going on with that data point. So you will end up with different types of labels and errors, and there will be disagreement. In segmented data, this might look like this, where you, for example, have agreement on these locations here, but then you have disagreement here or here. So in this case, this guy says green and this guy says white, and the other way around in this case. So there is disagreement on these two data points, but in general, they agree quite a bit. So there might be something about their opinions. So you can consider them as like insertions, deletions, and so on. In continuous data, when you like label like continuous data, like every 1/10 of a second, you want to get an opinion. You don't want to like segment each 1/10 of a second for each individual, like, or for each coder separately, but you actually want to have them watch a 5-minute segment, and they tell you in like starting second 15 to second 34, there's something happening, emotionally happening or whatever, and so they define the start and end points themselves. However, maybe they think of the start and end points differently. So maybe one coder thinks the start point is faster or earlier, maybe some guy says it's later, and so on. So you have like delays and lags and so on. Okay, so but you want to still quantify in both cases how well they agree on each other. And one way to get around this continuous problem is like very similar to like if you integrate a curve, you basically try to break it down into discrete segments that are of a certain length, and the more fine-grained you do this, the more accurate your investigations are. But obviously there's a trade-off between how fine-grained you want to do it and how broad you want to do it. Like, so the computational cost versus accuracy is an important consideration there. So there are thankfully a lot of measures that rate iterator reliability, and we can use some of them, and I introduce two today. One of them is really cool because it allows you to have 15 coders, and you evaluate like for every coder like together. Like you don't have to just so some measures just give you access to 2 coders at a time. Some measures as Krippendorf's alpha, that it's also available on R and MATLAB, etc. You can use however many coders you want, and they can actually have submitted different subsets of data as well. So you might have coder 1 and 3 code a subset, while coder 5 and 4 code a different subset, and you can still code or like assess iterator reliability. Just as an interpretation, high iterator reliability means that they have kind of like a similar scheme in mind that they think is happening, like they observe something similar, and you would, for example, if it's very expensive to have multiple coders on the entire data set, you want to first establish, oh, they agree on this subset of data, like 10 minutes of data, and now I let them go and do whatever they want, and I only need one annotator for the rest of the data. All right, so example here to calculate iterator agreement is also like if you want to just do a confusion matrix, you can assess like, okay, that they agree 70% in this case. However, this measure does not tell you like what the probability of agreeing by chance is. And the agreement by chance is basically brought in through the Cohen's kappa, where you basically now like measure based off of the chance agreement how it basically brings in the per chance agreement into the calculation to give you a better assessment of like, okay, what does this agreement actually really mean? And the per chance agreement in this case is just the probability of like randomly choosing one or the other, and that basically is 0.5 in this case. So so you can then calculate the kappa as such. Okay. So here just a couple of examples on how to do this, and now you're for this coder agreement in this case, your Cohen's kappa is 0.28, and that is pretty bad. As you can see, you want to kind of have a Cohen's kappa between like 0.5, 0.6, and 1, which is the maximum value that you can take. But as I said, this one only allows you to have 2 coders. So if you want to expand that, we can actually utilize this Krippendorff's alpha that allows you to have multiple raters, more generalizable for ordinal, nominal, and continuous values. So you have like a lot of flexibility here. And I think we'll mostly talk about this the next time. But yeah, I don't want to rush through this, but it's a very useful measure that works on, in this case, we have 5 annotators, we have different number of items. What we need to do is we need to compute the mean values, we need to compute the variances for each of those values. So the mean variance per item is 0.73, overall items and judges, and here we have the mean value of the variance, and basically what you compute is the average variance over each item that you observe divided by the overall variance of the observations and the mean values of the observations. And it's not super easy to code because you need to like allow for missing values and so on. But there are there's code available for Krippendorff alpha in MATLAB, SPSS, and R. Yeah, and you can consider like alpha values greater than 0.6 as a good agreement that you can use in your studies. We just submitted a paper where we had only agreement of 0.5, but like it was kind of expected. I think it will still go through, but this is kind of like just a rule of thumb. 0.6, 0.7 would be a good value to go ahead with. Right. So I'm not here on Monday. I'll try to see if Vishin can do a review session on Monday. And then on Wednesday we're going to talk about hidden Markov models.